All right, back. We're still on 287. We're on number 3. I have a comment about this. I also have a comment about number 4. It turns out that after I couldn't remember the name of that column for a couple of years, I edited the notes so that I could never forget again. We actually already did number 4, and that's awesome because that means that we're going to be able to kind of speed through some of this. First comment that I was going to make, second comment was actually about that. The first comment was the general from. Oh, I don't think so. The general form of the slopes we've been finding. What are you going to do? If only I could fix that typo, which I could, but will I? Probably not. The general from of the slopes we've been finding is f of 2 plus h minus f of 2 over 2 plus h minus 2. Simplify that as much as possible. So if you look at it, you can see that this is just the slope between 2 points, right? And the 2 points are 2 comma f of 2 and also 2 plus h comma f of 2 plus h. And then we have already filled in the column for h. H is just delta x. What's the change in x? So start at 2 and you end at 5, delta x is 3. So this is when we were doing the rotating things and finding volumes, we found delta x. Delta x is a huge part of calculus. Like you're going to find delta x's until you've gone crazy. All right, so let's see if we can simplify this as much as possible. So don't forget f of x is actually x squared minus 1. So this is really the quantity, not x squared. So f of x is x squared. Let me write it down. Okay, f of x is x squared minus 1, which means that f of 2 plus h minus f of 2 over 2 plus h minus 2 is just h, is going to be the quantity 2 plus h squared minus 1 minus, right, this is just f of 2 plus h minus f of 2 is 3 divided by h, okay, which is, all right, we'll expand 4 plus 4h plus h squared minus 1 minus 3 is minus 4 over 4, not over 4, over h. What happened to my h? It's like I scrolled while I was trying to write it. Now, if you look at that, you might recall me saying in the limits when we were doing those algebraically, at this stage, if everything that doesn't have an h doesn't cancel out, you are definitely wrong. So here, I just get 4h plus h squared over h, and that is the same as 4 plus h, as long as h is not 0, right? Algebra won't let you divide by 0. Calculus won't let you divide by 0, but calculus will let you deal with 0 over 0 because we can deal with limits. So this is consistent, this thing is consistent with the observation that we made up here, that the slope always just seems to be 4 plus whatever h was, right? So 7 is 4 plus 3, 6 is 4 plus 2, 5 is 4 plus 1. I could keep going, but I feel like you get it. So look at that. We simplified this, and we literally ended up with 4 plus h. That is definitely the pattern that's happening here, which is very cool. So we already filled in the table for h, because I jumped the gun, because I don't read ahead in the notes, which I probably should, but it's probably better to just go through them cold with everybody anyway. You know, like we're all in this together. Have I done it before? Yes. But do I know what's coming up? Maybe. All right, so there is definitely a general trend in h in the column. And you can see what we want is we want the 2 points to move closer and closer together. Ultimately, we want them to be the same point. So we need h to approach 0. So what we're doing is we're saying that h is going to approach 0. And h will always approach 0 in these problems, which is pretty good. So if we were to evaluate the limit as h approaches 0 of f of 2 plus h minus f of 2 over h, that's the same as, because we already did the algebra, the limit as h approaches 0 of quantity 4 plus h, which is 4 plus h is a continuous function. You can evaluate the limit just by substitution, because the limit equals the value of the function, because that's the definition of continuous, is 4. So That's the slope. That's part of why we've been doing so many limits. Like a lot of the limits we do are to justify discontinuities, like a jump discontinuity. The limit exists from the left, limit exists from the right. They're both finite, but they're not the same. Removal, limit from the left equals the limit from the right, doesn't equal the value of the function. Infinite discontinuity or vertical asymptote. The limit from the left or the right is infinity or negative infinity or whatever, or some combination of the two. A lot going on there. So limits can tell us about discontinuities that can justify them. Turns out limits can tell us the slope of a curve at a specific point, which is mind-boggling. So this, I'm going to write kind of in some words. This is the slope of f of x equals x squared minus 1 at x equals 2. It's exactly what it is. And that's weird. That's a new idea. The fact that something could have a slope at one point is very different from algebra, where you basically need 2 points to find a slope, and slopes are associated exclusively with lines. Calculus is not really the case. The notation for this might be to say that f prime of 2 is equal to 4, or you might say dy dx, the rate of change of y with respect to x, instantaneously. We don't need 2 points. That's why this notation is different. It's not delta y over delta x. Dy over dx means at 1 point and only 1 point. But the point can change, but 1 point. So dy dx is 4. These are just new notations, so I want to get them down. I think I'm going to stop here. I'm going to come back in another video, obviously, and just keep solving stuff. Like, we're learning a lot. We're learning limits. We're using limits now to find slopes. Where are we going to go from here? I don't know. We'll find out. So come back and I'll see you in the next one.